Okay, sorry if you're just joining us. Hey, you didn't miss much. Okay, so for Roman numeral 2, it says using the straight line from the graph, calculate the mass of the cart. So look, Newton's second law tells us net force is mass times acceleration, which means that mass is net force over acceleration. What's this? Is that a net force? No, it's not, right? Okay, so, but the issue is this. My net force is the force of the sensor, which is changing, plus the force of friction, right?
Yeah.
Tell me something important about the force of friction. That's a dumb question. It's constant, right? The force of friction is constant, right? So all that's going to do is it's going to shift the graph, depending on how you think of it, either left or right or up or down. But it's just going to be a shifting of the graph, right? Does that make sense? So it turns out that the slope of this graph is the same as if we'd actually plotted net force. All right? But that distinction between the fact that this is force as opposed to net force is going to be important when we get to the next Roman numeral, whatever that is. Follow? All right, so find the slope of the line and then take the reciprocal. Everybody good with that? Problems going once, twice, solved. Okay, now. So correctly calculating the slope, blah, 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 and find your mass. All right, cool? All right. Roman numeral 3. I wish they would have written more on this answer key here. To be sure, to be honest, I'm not 100% sure how they wanted you to do this. I have a good guess though. It says, using the straight line from the graph, determine the magnitude of the force of friction. So you have to use the straight line from the graph, and you got to find the magnitude of the force of friction. So let's go back to the graph for a minute. So if you notice, so if you extrapolate this graph, does everybody know what I mean when I say extrapolate?
Yes.
Extend it longer than it is. If you extrapolate the graph, you discover that our acceleration is 0 when the force from the sensor is not 0. In other words, you need to pull with more than 0 force just to create acceleration. Why? Because of friction, right? So do you guys agree that this x-intercept, not the y-intercept, the x-intercept should represent how much friction there is? Yeah, I guess technically, but it doesn't how do I want to say this? Yeah, I see what you're saying. Why do we not need to worry about that? So as soon as it starts moving, it switches to kinetic, right? Is everybody okay with that? Okay, so what acceleration? Well, anything above 0. So 0.000001. So there's sort of a limit there, I guess. You know what I mean?
Is that how you were going to say to do it? Or?
To find that x-intercept, yeah. There are other ways of doing it. My concern is that they don't use the straight line.
So you want
In the instructions, it explicitly say, using the straight line from the graph.
What if you use the math?
I don't know. That was what I was saying, is I don't love the way this one's set up. And, you know. Do you know what I mean, though, you guys? All right. Now, I think that using the straight line will boil down to the same thing you're talking about. All right. So let's try it. How would we find the x-intercept here? So what do we know? We know that our slope is, what did we found it a minute ago. What was the slope? Like 2.13 or something like that? Let's just, 2.13 inverse kilograms, right? Okay? And we're trying to find our x-intercept, right? God, I'm really unhappy with this problem.
I know, right?
What's that?
Yeah, me too.
Yeah.
Thank you.
So in some fashion, we got to find the x-intercept. We know points on the line. We know the slope. Do you guys agree that you can find the x-intercept from that? Do you guys want me to run through a way of doing that?
Do you use your best fit line or do you use one of the?
You use your best fit line. But remember, to find that slope, you had to pick points on your best fit line, right? So I guess my thinking would be you'd use that point and your slope to find your x-intercept. Follow you guys or no? Yes.
So they want you to use a calculator for that?
Oh, for sure.
No,
Absolutely.
I mean like you could.
Oh, as opposed to just reading the graph?
I mean it's a best fit line. Because you put in points and have it calculated one.
I gotcha. Yeah, so the way the answer key is worded, must be on the next page. So for correctly calculating the slope using the best fit straight line, note linear regression gives the slope. So if you do that, that's fine, but you just have to say using linear regression gives, follow? So if you guys know how to do that on your calculator, use linear regression, by all means do it, but tell the graders that that's what you did. Cool? All right. So yeah, I agree that Roman numeral 3 there is awkward. And I agree with you, Anthony. To me, it makes way more sense to just do F equals ma, net force equals net force, and solve for the missing frictional force, right? So I guess in lines of following the directions, I guess I would just say, from the line, we know the mass is this, and Newton's second law gives us this, and I think that would probably be okay, is my guess. You know what I mean? You just, my point though, you guys here, I hope I'm doing a good job explaining this, is that you need to make sure that you're following the directions and solving it the way that they want you to, not necessarily the way that always makes sense, right? Like we ran into one the other day with that, where the Atwood machine, right, where it would have been easier to solve it as a system. So you got to make sure you follow the directions. All right, so force dead. All right. Part C just wants you to apply Newton's second law to find the acceleration. So notice the grading on this. You can either use Newton's second law or you can just read it from the graph. You know what I mean? Just, what are you trying to do? You're trying to find the acceleration if the sense reading is 0.45. So just read from the graph and you'll get a reasonable answer too. Okay? Let's see, Roman numeral 2, the string breaks after 2 seconds. So you got to find the time it takes to stop. So after the string breaks, you guys, what should we be thinking about? What's our new net force going to be, guys? Whatever your frictional force was. Okay? So now, so what you need to do is you need to find the velocity at the instant when the string breaks. Once you know the velocity after the string breaks, they made this a little more complicated than they needed to. I probably would have just done acceleration is net force over mass, where your net force is your force of friction, right? And then once you know your new acceleration, then you can find the time by doing Vf minus Vi over your new acceleration, right? So I don't know why they combined these two things into one step. Cool? Is everybody okay with this? Am I like? All right. Okay. And then finally, part D. It says the experiment and analysis in the previous parts were repeated with a heavier car, with a cart with the same mass but a greater force of friction. Part 1, is the slope of the new line greater, less than, or equal? Well, what did we decide is the significance of the slope of the line before? It deals with the mass. It's the inverse of the mass of the cart, right? So if the mass of the cart hasn't changed, the slope shouldn't change, right? Make sense? All right? But because there's more friction, how's that going to affect our x-intercept? It's going to be bigger, right? You're going to need more force to get it moving, right? So it's going to shift everything to the right. Follow? Good or no? All right. Any problems with number 1? How did this go, you guys? Other than the weirdness of Roman numeral 3, I feel like this was all more or less straightforward. Do you guys agree? Everybody good?
Yep.
All right, Roman numeral 2. So I looked at this. I don't know, you guys don't care. All right. Am I safe in assuming I probably need... No. We're going to need to go through some of this. All right, so here's your free body diagrams. Again, notice how they labeled the force of gravity. All right, if you're adamant about using FG, then I would call this FG number 1 and call this FG number 2, where this is block number 1 and this is block number 2 or something. But just make sure that the graders know what your symbols mean. You know what I mean? All right. Everybody cool with why those are the only forces on there? I thought this was a weird question. Maybe they're just making sure you understand the fact that you can have motion without having horizontal motion without having horizontal forces. Maybe? Yeah.
Would different lengths of the, or magnitudes of the vectors be acceptable?
Yeah, absolutely, absolutely, yeah. I'm glad you said that. You didn't just hear him, he said, does it matter if you drew different lengths? I actually would encourage you to do that.
I meant instead of labeling them differently.
Oh, I gotcha. No.
Okay.
No. No.
So you should do it anyway.
Yeah. Yeah, and I would encourage you to be thinking about relative lengths. Do you guys agree that these two arrows should be equal and these two arrows should be equal? But theoretically, these two arrows should be longer than these two arrows, right? Sometimes they give points for that. This time, for whatever reason, they didn't, if you read through the rubric, but they do sometimes. My belief / hope is that, like they did in the one yesterday or the other day, they'll say, make sure you draw them appropriate lengths. But better safe, right? And it's not that hard to just go, oh, well, this is going to be more force. I'll draw the arrow a little longer. Cool? All right. Okay, so is everybody good with A? All right. So B wants you to find an expression for the speed of the blocks immediately after the collision. So what should we be thinking about there, you guys? What physics concept? Conservation of momentum. Anytime you see a collision, automatically you should think, oh, momentum's going to be conserved. Always. Clear? All right. So for part B, let's see what kind of detail they give us. Yeah, they're basically saying that the momentum of the 3m cart before the collision has got to equal the combined momentum after the collision and solve. So you get 3/5 your starting velocity. Cool? All right. So part C wants an expression for the kinetic energy of the two-block system after the collision. Well, we just found an expression for the velocity after the collision. Kinetic energy is 1/2 mv squared, so you just plug in your numbers, right? Yeah.
Yeah, so energy is also conserved then, right here.
I don't know. What do you guys think? Is energy going to be conserved here?
No.
Yeah, it's not. So anytime your two objects stick together, that's called a, I think I've been saying completely, I should have been saying perfectly, but whatever. Perfectly, completely inelastic collision. That's actually, it's, the objects sticking together is the situation where you lose the maximum amount of energy. There's no way you'd lose more energy than if they stick together. What word do you have to see in the problem to know that the energy is conserved? Elastic. Okay? Elastic. If it says it's an elastic collision, that means that your total energy is conserved. Here it is not. Clear? No, it's just elastic. Yeah, so there's elastic means energy is conserved. Perfectly inelastic means they stick. And then just regular inelastic is somewhere in between. I know, I hate that terminology too. I agree. All right, everybody good? Right, it should be perfectly elastic, right?
Say that again.
But it's not. Sorry?
Can you say that again?
Say what again?
Elastic is all.
Elastic means that all of your energy is conserved.
Yeah.
Perfectly inelastic means that they stick together, so you lose as much energy as you're going to, or as you could, I guess. And then inelastic means they don't stick together, but you're losing some energy. Cool? It's in your notes. I don't mean that in a snarky way, but like if you forget it, like you can go back and look. All right, everybody good? You guys, do I need to write that out? You guys want me to write it out real quick? Everybody got it? Okay, cool. All right, so is everybody good with C? All right, now, part D. Oh, question? I'm sorry.
About C, it doesn't seem like it would be, but is it fine if I pretty much had what they, for the answer, I had 1/2 5 M3 because B not squared instead of actually simplifying.
Oh, I gotcha. It does say an expression. I don't think that it matters if you simplify it or not. For safety, I would simplify. You know what I mean? Yeah, and unfortunately, I haven't sat in on any grading sessions yet, so I'm not sure. The conference I went to last time, some of the things they were adamant about, like writing G equals, which to me is like duh, and then there's other things that to me were not obvious that they didn't do points off for. You know what I mean? So, I don't know. I would always lean in the direction of better safe than sorry. You know what I mean?
Yeah.
So, all right, is everybody good up to part C? All right, part D, am I safe in assuming I should go over D? Derive an expression for the maximum distance the spring is compressed? Yes? Okay, so here's the deal. Remember I told you guys, I said, oh, this is another one of those drag force problems, right? So when I say a drag force problem, what makes it a drag force problem is that the resistive force, whether it's drag force or whatever, is proportional in some sense to the velocity. Okay? And I saw this problem has this. And I saw this and just thought, oh, the force is variable. It's a drag force problem. But it's not, because here the force doesn't depend on the velocity like it does for drag force. It depends on the position like it does for a spring. Make sense? Okay, so for a regular spring, and so this is worth noting, you guys. For a simple spring, sorry, I guess it's technically called an ideal spring. It's so bad with vocabulary. For an ideal spring, we know the following two things. We know that F is equal to Kx, I guess negative, right? And we know that the potential energy stored in that spring is 1/2 Kx squared, right? For one awesomeness point, does anybody remember how we got this equation? By taking the integral of our force with respect to x. Follow? All right. Now this problem has a spring, but it is not ideal. Oh. So here we've got a non-ideal spring that says ideal, and it tells us that F is it B or beta times x cubed, right? So how do you think we're going to find our elastic potential energy? Integrate. Okay? It's in the problem.
Did it? Oh, okay.
Yeah. So if you read up at the top, it says the spring is nonlinear and exerts a force of f of x equals negative dx cubed.
Okay, thank you.
Cool? Follow you guys? All right. So with that in mind, here's what we know. So in part C, we figured out that the kinetic energy of the system, we found out that the kinetic energy of the system immediately after the collision was this number, 9/10 mv0 squared. Cool? All right, now, to do part D, it wants to know what is our maximum x, and they call that D, right? And they want to know what that value is. All right? So at maximum compression, tell me something important about the energy. All EPE, right? So we need to come up with an expression for that EPE, right? So remember, you guys, the work done by a conservative force is equal to the opposite of the change in that potential energy, right? So that's how you get rid of the negative, because of that negative sign here. Cool? So, as we said here, to get from here to here, we integrate. So to find this elastic potential energy, we're going to integrate and get rid of the negative. Follow? Notice, if you think about it this way, you don't even... Well, never mind, I don't want to do that. Okay, so let's integrate it. So our elastic potential energy should be the integral from 0 to x of bx cubed, right? With respect to x. Follow? So, let's see. What would I have to take the derivative of to get x cubed? What is that, 1/4 x to the 4th?
Yeah.
So I think we need b over 4 x to the 4th, right?
Yeah.
And then evaluating between 0 and x is just going to give you that x.
Problem
Go ahead.
had us in the problem it had us make x capital D. Would that like change the like if we hadn't if we didn't state it with capital D, if we had it like as x on the AP test, would they mark us out?
That's another one of those better safe than sorry things. Yeah, I would write d equals with your answer there. Cool. So also acceptable, I guess you could call this d, right? And that would give you the elastic potential energy at point D. Cool. And that would make this d. Okay. All right. Sorry, I have too many papers here in front of me. So, all right. So then to solve it, then you just go. So our kinetic energy. Equals. And then solve for d, right? And you get this mess. So multiply both sides by 4. You're going to get, what, 36 over 10, which is the same as 18 over 5. So 18 fifths mvo squared. We got to divide by b in here somewhere. Over b, and then you got to take the 4th root, right? Get rid of the 4th. Cool? All right. So I think the big thing here, I'm guessing this is probably where people struggled, is are we all good with how I knew I had to integrate? Cool? All right. Was that the end of that one? No, it was not. Okay, let's see. Roman numeral 1. In which direction is the net force, if any, on the block of mass 2m when the max is at its maximum compression? So here, do I have the drawing up? I don't think I even have the drawing up anywhere, do I? So the block is moving to the left, right? So at that instant, there's a bunch of ways you can say this, but in some fashion, you need to justify the fact that the spring has to be pushing the block to the right. Does anybody want to share their answer and make sure it's okay? Is anybody unsure of their answer? So there's a lot of ways you can do it. So here are some acceptable answers. Immediately before that point, which way is it moving? To the left. And at maximum compression, it stops, right? So to stop something moving to the left, you got to push it to the right. That's an acceptable answer. Also acceptable. At maximum compression, the displacement is negative. Since F equals negative bx squared, the force has to be in the opposite direction. Okay. And then that would be acceptable. I don't know. Anybody have anything other than that I didn't just list? Okay, cool. Roman numeral 2. More force on block 2 or block 3. Well, they have the same acceleration, right? So the block with more mass has to have more force on it. Cool. Roman numeral F. I'm sticking with it. Deal with it. Simple harmonic motion or no? No. What's the definition of simple harmonic motion, you guys? Force is proportional to the displacement. So if it had been F equals kx, it would have been simple harmonic motion. But since it was kx cubed, it is not simple harmonic motion. Clear? All right. Any problems? All right. 3 was tough. You guys just want me to go through all of 3? Is that a safe assumption? Yeah? All right. All right. So, here we go. So you've got this uniform rod, and the idea is as the disc spins, the spring has to exert more force to provide the centripetal force to keep the block going in a circle, right? Okay? And so you need to ensure that the force of the spring is always equal to your centripetal force. That was kind of the premise of this problem. Does that make sense? Okay, so thing one, we need to ensure that the centripetal force is equal to the force of the spring. Thing two, equations for centripetal force. Centripetal force is mass times centripetal acceleration, right? And we usually have done this. But that's kind of a pain in the A in this problem because we're not, for most of the problem, we're dealing with the angular velocity of the disk, not the linear. So, yeah, so remember, AC can also be written as omega squared times r. So this equation is going to be your best friend in this problem. Cool? Everybody good with that? All right, so with that in mind, let's see what we can do here. Roman numeral A wants an expression for the spring constant of the spring. So, for part A, this is number 3, for part A, we're going to start with what I just said. We know that the force of the spring has to equal our centripetal force, right? So, where is it? Oh yeah, so it does say ideal spring. Maybe, I don't know if I've stressed this or not, you guys. Ideal spring means F equals Kx. Okay? Yes. All right, so we have to have Kx equal to our centripetal force, which we just decided was m omega squared times, what's my r here, you guys? Oh, well, let's just do this. So do you guys agree with that, other than the fact that I got to fix my variables a little bit? Right? Centripetal force, I'm sorry, spring force equals centripetal force, right? Okay, so spring force. What's x in this problem? In general, what does d represent, you guys? Did I just ask the wrong question? Well, in general, what does x represent? Sorry. It's how far you stretch the spring, right? So if this is some length, then x is the difference between that length and that length. So how much did the length of the spring change between the two drawings, you guys? D over 2, right? So I've got k times d over 2 equals m omega squared times what's r? Is it 2d? 2d, right? So you got d for the rod plus 2 half of d's, right? So 2d. Cool? All right, and so what do we want? An expression for the spring constant, right? So multiply both sides by 2 and divide by d, and you get k equals m omega squared times 4, and the d's cancel, right? So I guess let's put the 4 up front. There you go. Everybody good with that? All right. Let's see. Part B, Roman numeral I. Determine an expression for the rotational inertia of the block around the axis of the platform. Well, the block is very small compared to the size of the rest of the platform, right? So how should we consider the block? Point particle, right? So what's the rotational inertia for a point particle, you guys? mr squared. That's a thing you should memorize. So for us, it's m times the radius is 2d squared, so you get 4md squared. Follow? All right. Roman numeral 2 wants an expression for the rotational inertia of the entire system. So, let's see. So we just found the block. We just found that. That's 4md squared, right? For the rod, it tells us that it's mr squared, mr times d squared over 3, right? And it tells you what mr is, right? It's 3m. So the only mass that you should be using here, you guys, is m, as in the mass of that block at the end. Okay? So this becomes 3m d squared over 3, and the 3's cancel. Am I going too quick, or are we good?
You have to add them.
Eventually we're going to add them, yes, but we're not there yet. Everybody good? So I got the rod and the block. Everybody good up to there?
Yep. Yep.
All right, and then similarly, you got to do the platform. And it tells you that that is the mass of the platform times r squared over 2. So the mass of the platform is 5m. The radius is 2d, all over 2. So simplify that, and you get 10 md squared. And like Margaret said, add them all up, and you get, what, 15 md squared? Everybody good? Too fast? Problems? Concerns? All right, part C, determinate expression for the angular momentum. What's the equation for angular momentum, you guys? L equals I omega, right? Well, I just found I, so tack on an omega after it and you're done. Okay? Please notice when you do these problems, you guys, it will always say, when it's just all letters like this, it'll say express all algebraic answers in terms of, and they'll give you a list of variables. Make sure you only use those variables. Okay? The only other thing acceptable is physical constants like pi, g, I think that's it, capital G maybe if you're doing like a gravitational force problem. Cool? All right. While the system continues to rotate, the small mechanism in the pivot moves the rod slowly until the center of the rod is positioned in the axis. So in other words, it's sort of pulling everything in towards the center, right? The same constant angular speed omega is maintained by the motor driving the platform. When I first read this problem, or when I first looked at this problem, I thought it was going to be a conservation of angular momentum problem. What has to be true for it to be conservation of angular momentum? What has to be true for it to be conservation of regular momentum? No external forces, right? So what has to be true for it to be conservation of angular momentum? No external torques, right? It says the same constant angular speed is maintained by the motor. That's an external torque, right? The motor is going to provide the torque to make the motor do what it wants to do, or to make the platform do what it wants to do. Good? Does that make sense? So we're still spinning at an angular velocity, omega. So to do part D, it says derive an expression for the distance x. The spring is stretched when the rod reaches the position shown. So I think this is just another centripetal force equals the force of the spring problem, right? So my centripetal force is m omega squared times my radius, which is d plus x, I believe, right? Convince yourself of that. Is everybody cool with why it's d plus x? You got half of d because of the rod. It's half of the rod. And then the original length of the spring is half of d. And then plus x, right? Okay, and that's got to equal the force of the spring, which is kx, right? And then solve. Cool? All right, any problems there? All right, ooh, we're going to finish this. Part E, is the angular momentum of the entire system increasing, decreasing, or staying the same? Well, look, E, angular momentum is I omega. Our omega stayed the same, didn't it? What's happening to I? It's decreasing, right? Because we're pulling all of our mass closer to the pivot point, right? So, if this decreases, this decreases. Cool?
Yeah.
All right, F. In order to keep the system rotating with constant angular speed, is the motor doing positive work, negative work, or no work? So there's two ways you guys can be thinking of work, right? In terms of linear, work is force times distance. For us, we're talking angular, so we want to think torque times change in theta, right? But that doesn't help much here because I don't know how much torque the motor is providing. I don't know how far the wheel spins. So this is kind of a dead end. All right? What is work? Like, what does work mean? What are you doing when you do work? Changing energy, right? So in this case, what kind of energy are we concerned with? Rotational kinetic energy, right? So rotational kinetic energy is 1/2 I omega squared. Omega is fixed. If I decreases, so does my rotational kinetic energy. We're losing energy, it must be negative work. So,
And you know, why do you know the I is decreasing? It is
so you could calculate it, but it would be way more cumbersome than you need to. All right. So remember we talked about a figure skater pulling our arms in and spinning faster. Why does that happen? You remember? Bless you. Okay. So remember, your rotational inertia depends not just on the mass, but the positioning of the mass. All right. And in general, the farther your mass is away from your pivot point, the more inertia there is. Okay. So when the mechanism pulls that mass inward, that's like the figure skater pulling her arms in. She's pulling the mass closer to the center. Follow? If you think about it, the rotational inertia of a particle is mr squared, right? So when I pull that in, I'm decreasing this radius for all the particles. Follow? Everybody good? Okay. And then finally F. No, finally G. On the block, draw a single vector representing the direction of the acceleration. So you're given this big thing. Here's your kind of coordinate system, and here's the block, right? Okay, so there are two types of acceleration. It's moving in a circle, and therefore there has to be centripetal or radial acceleration, right? So there's got to be radial acceleration, right? And since the angular velocity is constant, remember you guys, v is omega r, right? If this is staying constant, what's happening to the linear velocity, you guys? Your angular velocity is constant. What are we doing to the arm though? We're pulling it in, right? Right? So your radius is decreasing. That means your velocity has to be decreasing, right? So if it's spinning this way, that means my linear velocity is this way, but it's decreasing, which means there's a tangential acceleration pointing that way. Does that make sense? So it's being pulled inwards, centripetal acceleration, and slowing down, tangential acceleration. So your overall answer should be the vector sum of those two. So here's your answers, that red arrow. Because it says draw a single vector. So you don't want the two greens, you want the red.
So it is slowing down.
It is slowing down. The linear velocity is decreasing. The angular velocity is constant.
How is maintaining theta? Or not theta, excuse me, omega.
Yeah,
but the radius is.
your omega is fixed, but as the block B gets pulled, I almost said it, as the block B is pulled towards the center, your radius is decreasing, which means your linear velocity has to be decreasing. Does that make sense? Sorry, I was laughing at your shirt.
Oh, yeah.
Cool, you guys? All right. So the bell's going to ring here in a minute. So real fast in this.